Okay, so basically what I wanted to cover is the field of advanced feature engineering. And I've tried to do this in such a way where there's going to be a very low emphasis on code and a much higher emphasis on strategy, so that regardless of the platform that you're currently using, you can take the most advantage out of the presentation today. I look forward to answering your questions and comments at the end of the presentation. If I happen to miss one of your questions, please let the team know, and I'll be responding to any emails I get before the end of the day and try and get back to you over the next several days. So let's get started. So I wanted to start with a basic introduction to where have the tips that we're going to be discussing today been used before. I see a lot of presentations, some of which are truly fantastic, and some of which I have to raise a question or two. And that's because I always want to know where the tips that are being discussed originated from, and to get some idea of where they've been tested, so I have some type of confidence in the results that are being presented. So different portions of this have been tested at a number of corporations that I've either worked with full-time or have served as a consultant for, including IBM, Audi, AARP, the FDIC, Mercedes-Benz, PayPal, the Royal Bank of Canada, and Morgan Stanley. Now, it's important to note that all the views expressed here in this presentation today are solely my own and should not be taken as being those of current or past employees, clients, or anybody else. So why do we care? Let's talk about the rising challenge that most people aren't discussing. Now, if you remember about 6 years ago, there was a very big article that came out from a company called Nucleus Research that was indicating that the typical return on analytics in general was somewhere between 900 and 1200%, which is a ridiculously high amount. So essentially, their net conclusion was it was about $13 for every dollar that was invested. And this is one of the reasons why there has been such a boom in the field of analytics, big data, and artificial intelligence. And that's fantastic. I don't know of a whole lot of other endeavors or fields that one can pursue that can approach anywhere near that type of return. So that's great. So what's the issue? Well, if you all are familiar with a company called Gartner, a consulting firm that operates globally, they last year applied what they call the Gartner hype cycle for artificial intelligence. And if you take a look at the graph here, you'll see that they break timelines of a new technology being introduced into 5 different phases. An innovation trigger, and then unfortunately a peak of inflated expectations. The third phase is what they call the trough of disillusionment, in which case people are less excited about the technology. And now a lot of doubts get raised. They're not really sure whether this was really all that was supposed to be cracked up to be or not. Then comes the 4th phase, which is the slope of enlightenment. And 5th, the plateau of productivity. Now, I might argue that these aren't exactly the same names that I would apply to these things, but essentially it gives you a good idea of the flow of what happens with all new technologies when they're introduced to the market. Here's the challenge we're facing right now. If you take a look at the big red box, we're currently suffering from what I would call the trough of disillusionment. Okay, so AI is out there, everybody thinks it's fantastic, it's going to solve all the problems of the world, especially when Google made its big announcements after its research that was released in 2010 for deep learning, which indicated that all sorts of problems that couldn't be solved previously now could be solved by creating especially deep neural networks, hence the term deep learning. Okay, but what happened? Well, few people seem to notice that just a few years back, Google announced that it was stepping back somewhat from artificial intelligence, and that no, AI was not going to solve all the problems of the world, and that other approaches were still necessary, and that they were basically issuing a small mea culpa in terms of pushing the technology so hard. Well, if that's the case for Alphabet and Google, you wonder what's happening with other companies. Is this not as promising as we thought before in other areas? Well, unfortunately, that seems to be the case. Let's take a look at a couple of slides real quickly about recent headlines that have come out, most of which last year. The AI failure rate, according to VentureBeat, is 87% of data science projects never make it to production. That is a horrific failure rate. So that means that only 13% of the data science projects ever make it into production? Something seems wrong there. But that's not the only one. If you take a look at some research that was done by BARNRAISERS all the way 5 years going back, where big data, which was the big phrase back in that day, was going to be the solution to everything. And the questions started coming out and saying, well, I don't seem to be getting the ROI that I thought I was going to get. All right, back to Gartner again. Okay, now 85% of artificial intelligence projects will, quote, not deliver for CIOs and organizations. All right, so this is starting to look particularly painful for a lot of what we're doing. And last, you had another research project that was done from a company called Designing for Analytics, which indicate that the models might have been right, but the projects don't ever make it into production from their research either. So this has been a pretty huge disappointment for a lot of organizations. All right, so what does this have to do with feature engineering? Well, I'm going to get to that in a moment, I promise. Let's take a look at the analytical approach of how organizations try and move from big data, analytics, data science, artificial intelligence into results. And I'm really fond of this particular graphic that I wish I could claim was my own, but it's not. But as you can see, you've got 5 chevrons in a row: data, analytics, insights, action, and value. The point being, if you start at the right-hand side and your ultimate goal is to get value from your research, your project, your analytics, you have to be able to have each of the 4 chevrons that appear previously to this. So to get value, you need action. To get action, you're going to need to have insights. To get insights, you need to have done some type of analysis. And to have analysis, you need to have a starting point of the data. Well, these first 3 components, which are clearly critical, are all components that involve feature engineering. So if you don't have the feature engineering components in the front, you can't get to the value on the back end. Is there a relationship between that and the overall problem that we might be facing? If you take a look at this process diagram that was created by the folks at SAS, I'm particularly fond of this one. Now, there are lots of different approaches on how to do data science process flow, but this one I particularly liked. And if you take a look again, within the red box over here, you'll see that the steps for data preparation, data exploration, transforming and selecting variables take up most of the right-hand side, all before, hold on just a second, you get to build the model. Now, obviously, you have to identify and formulate the problem correctly, but you need to have these 3 steps in place if you're going to be able to get, again, to get the model executed. Now, this is just an example task list that I made up, but it gives you a basic idea. Again, if you were to convert each of the 8 different components of the previous diagram and sort of line them up and say, well, what are the components that involve feature engineering? You would have that. And if I can stop hitting the wrong buttons, this presentation is going to go a lot more smoothly. I apologize, folks. All right. So anyhow, you have all these components in here of the different steps. Now, so why is feature engineering and the things that I keep putting red boxes around so important? Well, you need to focus on where you're going to get the greatest gains to be able to make sure that you're going to get your program across the finish line, that you're going to be able to execute this, and you're going to be able to get your ROI back. Well, if you take a look at this diagram that was put together, 82% of all the work of data scientists comes from building the training sets, cleaning and organizing the data, collecting data sets, mining for patterns, in other words, building the model and refining the algorithms, these 2 steps here, collectively are only 13%. And there's another percent that's 5%. All right, so if we're going to try and figure out what is going wrong with our overall process and our ability to implement these models, it might make sense to focus on where 82% of the effort is. And you can also see that it's critical for achieving value. All right, So that's a pretty good hypothesis, but is this really true in the real world? Is feature engineering and the data prep steps really all that important or not? Well, if you take a look at some of the research done by Dr. Pedro Domingos of the University of Washington, he came out with a book several years ago called The Master Algorithm: How the Quest for the Ultimate Learning Machine Will Remake Our World. All right, well, with a title like The Master Algorithm, you would suppose that algorithms are what he's into and what he thinks is most important. Except that's not the case. His famous quote is, "Some machine projects succeed and some will fail. Where's the difference?" Easily, the most important factor is the features used. All right, so here's the guy who's supposed to be Dr. Algorithm, and when he talks about this as an overall process, he says that features are actually more important. Okay, well, now we might be onto something. Similarly, there was a huge research study that was done by a bunch of folks who reported in the IEEE Intelligent Systems newsletter back in 2009, called The Unreasonable Effectiveness of Data. And this was back in 2009. And once again, the research all was supported to say that data, and more quality data, can be much more powerful than clever algorithms. Now, part of the problem here is if you look at the popular press on data science, machine learning, and typical other representations of the field, you will see tons and tons of information on algorithms, deep learning, convolutional neural networks, reinforcement learning, LSTMs. All those things are great. And there are certain cases where you absolutely need to select a particular algorithm to solve a problem and nothing else will do. The example that I think of most often is if you have a case of P greater than N. In other words, you have more variables than you have records. In those particular cases, you're going to have to focus on a very specific type of algorithm to be able to solve that problem. If you're going, SVMs, if you're going to be able to find kittens in YouTube videos, you're probably going to have to use some type of deep learning. It's very difficult to get comparable performance in any other type. But for most of the problems that we need to solve, who's going to buy? Who's going to try? Who's going to attrite? What's going to happen with a typical classification business problem? Lots of different models might be able to solve that in different algorithms if the feature engineering is done correctly. All right, so what are we trying to do here? I'm going to break it down into a couple objectives and talk about how feature engineering applies to each of those objectives in the model building process. So objective number one, in any data set, pretend that what we have on the left is our data set, you've got two big components. One is the signal that we're trying to find, and the other is the noise. And if you're not careful, while you're trying to get the bottom part, the signal, you can end up masking it with a bunch of the noise. And also, the model can try to adapt to the noise as opposed to focusing on identifying the signal. That's going to be a big challenge, and we need to find some type of method in feature engineering to break the two apart successfully. Second objective, there are lots and lots of objectives with feature engineering and for data preparation, all the way from exploratory data analysis up through the actual feature engineering process that we need to be able to handle. And if you want to start a bar fight among statisticians, an easy way to do it is to go in and say, hey, what do you think the most important objectives are? But what we're going to say is that we're going to focus on these six, and I'm going to refer to them as the big six. One, how are you going to handle outliers, especially if you're using some type of regression-based approach? Two, how are we going to handle missing and null values? What's going to be our process for replacement? Lots of different theories on this. An almost endless stream of PhD research projects have been based on how to handle missing values. Third, input scaling. How are we going to take each of the individual inputs and put them on a common scale to eliminate some typical issues? Fourth, dimension reduction. What are we going to do to take the overall input space and reduce it into a format that is going to allow us to reduce those dimensions down to the ones that are truly key for the final analysis? Five, How are we going to handle smoothing, if at all, especially when you have time series analysis? And last, what are you going to do with features that are going to show up as nulls, zeros, or not a number? Similar to the missing values, but this is a case where if missing values is we just didn't find them in the research, whereas the null values are the ones that were supposed to be there, but for whatever reason don't appear. Objective number 3. Simplification is really important. So both of these quotes have probably been misattributed. So I'm going to start off by saying that if you actually do the research on places like Bartlett's for quotations, they will argue whether these quotations actually come from these two individuals. But for purposes of our discussion, we're going to pretend that they do. Leonardo da Vinci was supposed to have said simplicity is the ultimate sophistication, and Albert Einstein indicated that everything should be as simple as possible, but no simpler. So let's go to the rationale. Complex systems have many more fail points than simple ones. So if you're going to define a process, you want to come up with one that's relatively simple just to reduce the number of places where it can break. And one of my favorite sayings about this is, if you don't understand it when it's working, how are you going to fix it when it breaks? If you have an algorithm, for example, that's so complicated that you don't fully understand it or can't effectively explain it to someone who's helping you debug the project, you're going to be in a world of pain. You don't want to do that. So get an understanding of what you want to use your model for, and then work backwards to see how much you can simplify it along the way. Feature engineering can be a giant component of that. All right, so now to the tips and tricks. I've got 10 here. There are probably more. If you follow me on LinkedIn, I'll be happy to supply additional ones, and I'll do my best to answer your questions at the end. All right, here we go. Now, the first tip may seem a little silly, but think of yourself as a fine watchmaker. Think less assembly line, more fine craftsmanship. I do get a little tired of folks that I run into who think that everything in the universe can be solved by just adding a couple more Python libraries to the end of the process, and somehow magically a miracle will come out the other end. Or alternatively, the tools that say, oh, you don't need a data scientist in there at all. I'll give you an example. I was actually in a presentation at a very large financial services firm that I know that you would recognize the name of. And the person who was presenting the software indicated, nope, when you present us the features, you don't even have to tell us what they are. You don't have to name them. We don't need any labels. Just send us a bunch of columns and we will be able to identify the correct answer without knowing anything about it. Well, that sounds really impressive until you actually go to test the software and find that all the wheels come off. I am all for automating processes that can be automated, and I think you should take advantage of that. But before you decide to take the human being out of the loop, make sure that you considered what the impact might be if you're trying to build a watch without the watchmaker. Second, try to simplify relationships to either binary flags or straight lines. Please remember, computers are not smart, even though we call this artificial intelligence. What computers are highly fast and highly efficient. That's where their strengths are. But if you make a relationship between your target variable and your predictor variables easier to identify, the model will perform better, almost guaranteed. So think about as much as you can utilizing flags or simple linear relationships, and that's going to help enormously. Third, tips and tricks. The pieces that you can automate are at least to test different transformations based on what the original variable has. Now, over on the left, you'll be able to see 3 columns of basic tests: linear, power transformations, and inverse. Parabolic functions, demand functions, exponential functions, all of these might behave differently. If you're just going through EDA and you have to take a guess as to which to use, this is a starting point. I am not suggesting in the feature engineering that you automatically take the results of this. What I am suggesting is for a lot of continuous relationships in your data, you can automatically set up a process in your pipeline on the front end to do some of these conversions and add incremental variables on the front end. Then test out for each variable family which of those transformations work the best. So in other words, here you're combining the expertise of yourself as the model maker with engineered feature pipeline that allows you to do some of these transformations on the front end. Number 4, I want to introduce an idea of changing people's mindset. A lot of people talk about ensembling for final models, and that's fantastic. And ensembles do extremely well. If you look all the way back 5 years ago, which seems like an eternity ago, back at what was winning either in the KDD Cup or the Liberty Mutual contest that was on Kaggle, you'll find that what you'll see is that they have huge numbers of models all ensembled together to be able to provide the results that they were looking for. So the one on the left I find particularly impressive. Each one of those tiny little boxes is a different version of algorithm ensembled together. Okay, great. But let's take a step back. If the overall purpose of a model is to be able to do ensembling of different relationships, what if we considered each individual variable as a potential model of its own? In other words, what transformation could we apply to an individual variable as if it was a model of that variable? Now, 80% of these transformations are going to get thrown out, and you have to really be okay with that. Heaven knows I am. There was a time early in my career where I wanted to outguess the data and to say, hey, I absolutely know what's going to be important here. It's this variable, that variable, and the other. In fact, earlier in my consulting career, I went into another financial services firm, and they indicated that, well, you already know what the variables are. Just tell us what we are. We'll pull those out. We'll put them in the model. Even though I'd never worked on their problem before, I'd never seen their data before. That's not true. So obviously that wasn't true. But if you can consider each individual variable and feature a possible model unto its own, you'll have a very different approach. If you end up throwing 80% of it out, that's fine. What matters is what gets to the final model. Tip number 5, target mean encoding. If you're going through and identifying all the different variables that you have, especially if you have a categorical, you can actually change that categorical variable. Let's say we had values of A, B, and C. And in A, 3 out of 4 cases were right, so a 75% target rate. In B, it was 2 out of 3, so a 66% target rate. And C, 2 out of 2, 100%. Now, those are ridiculously tiny samples, but it's the only way to get everything to fit on a single page. And this is all courtesy of H2O.ai. I absolutely recommend that you check out a lot of their publications and training. All right, so if we have converted everything over to a target mean, then those become the engineered features that go into the model. Number 6, if you look on the left, you see a typical example of how you would bin a continuous variable into different categories and then use the bins. The problem is, as you can see over here, you have very different populations and you have very different frequencies as you see over here. So what happens is your bins end up as, for lack of a better phrase, kind of lumpy. One of the things you can do, however, instead is to run a decision tree against your target variable with an individual feature. And then what you do is that each leaf node, as you see here at the end, will have its own target rate. What if you actually took the tree to convert the original input and then took the results of those, and that became your borders for your bin? So in other words, you're not forcing a group of data into these type of ranges where you don't know if they're true or not. You've actually used the decision tree to determine those boundaries. Number 7. Lots of people are fans of random forest for a lot of different reasons, but essentially it's just a group of decision trees put together. But there are 2 things that people seem to miss in many cases with random forests. Number 1, random forests will actually automatically create a feature importance list. You can use that for any type of model in terms of you're trying to do dimension reduction. And number 2, remember that each one of these trees, just like I referred to on the previous slide, can be a decision tree or an engineered feature of its own. You could actually use this in terms of your process to be able to fix things that you had issues with. So in other words, you can take both of these outputs as part of your overall modeling project and use these as engineered features all their own just by running a random forest in the beginning. Number 8, dates. Especially if you're trying to look at buying behavior and especially if you're looking at B2B buying behavior. Dates have all sorts of information in them, and I'm not going to read the whole list to you, but the idea are the cadence, the velocity, what's the day of the week? Was it a holiday versus not a holiday on that date? Each one of these is an engineered feature. What about the geography to make sure, is it a holiday in that local area? Obviously, different types of holidays are separated in different areas of the world at different levels. Where are you going to have shopping spikes? Was it near Christmas? Was it near Mother's Day, et cetera, and so forth? And also pay a lot of attention to difference in dates, comparison to the target event, and watch out for leakage. You want to make sure that you only use data that you knew prior to the model being scored. Number 9 is kind of a weird one. If you're looking at a lot of continuous variables that may have a mode of 0, for example, you're trying to do fraud detection, a lot of those financial transactions will have lots of zeros in them. Well, one thing you may be interested in, let's say you are doing a fraud model for somebody who just bought a diamond bracelet at Tiffany's Jewelers. You may not care whether the person in the past has bought 7, 8, 9, 10 diamond bracelets at Tiffany's. And there's probably a good chance it's the same person that's safe. What you're probably most interested in is, was it 0 or not? Has the person ever been to Tiffany's before? Have they ever bought a diamond bracelet before? 0 has a more powerful relationship as a flag than it might be as a continuous input. So consider that transformation. Number 10, if you actually go through and review all these different pages, you'll notice that decision trees show up in different ways and a lot of the different tips. If you actually apply all the steps on this page just by using decision trees for your individual predictors on the front end, you'll probably end up with a pretty successful project. And I am running out of time, so I'm not going to read all this to you, but I'm happy to answer questions on it. And folks, that's it. Do you have any questions?
Thank you very much, Scott. Can you hear me now?
Thank you.
Yes, we have question. Thank you. Really interesting tips. I can feel and connect with some of them with several years of tears and the scratches we have in the bag.
Absolutely.
With zeros, I can connect with many of them. So if you don't mind, I'm going to start with the questions we have already in the Q&A.
Fantastic.
And I'm going to read it through, and we can work it out together. So the very first one's coming. What do you think are the leading reason that the production failure rate for data science project is so high? Do you think this failure will lower as the field matures within business sectors?
Yes, because if the field doesn't start handling that problem, there's not going to be a field anymore. You can't continue to have an 87% failure rate. I think the biggest cause of that is that the data science team is separated from the implementation team, and that the data scientists don't take the time to work out the delivery schedule and the delivery details before they start the model. What they do is they go and they do a lot of research. They go off for 6 months. The world has changed. They come back. The data is no longer relevant, and they don't have a sound implementation plan. That's why most of these projects fail.
Good. Let's go to the second question, which is, if you had to give one piece of advice to people just starting out on the road to the engineering, what would you tell them?
If you want to build models with ease, always start with decision trees. How's that? I got one to rhyme. I was so proud of myself. Yeah, that would be the one that I would start with, just because it's very easy to follow. And there's so many implementations of it, and you can actually do the implementation with just a SQL statement. You don't even need Python for any of that. It's also a great way to go back to your internal client and say, hi, I see this set of conditions and this set of outcomes. Does this make sense to you? And they can say, wait a minute, you can't use that. That's not a field we have, or we don't use that anymore. You eliminate a lot of problems up front, as opposed to saying, hi, here's my 600-layer deep learning model. Do you think this looks right to you? That's very difficult.
I'm going to top up this question with the question I had in my mind, is that if you are going to run a supervised versus unsupervised learning, then how do you see these tips and tricks? Are they going to be almost similar, or is there going to be any difference in
It
that?
would probably be different in that you can actually use unsupervised learning to learn a lot about your data set before you even do feature engineering. You can take the clusters that come out of an unsupervised model and use that as an input to a supervised learning model.
I see. I see. Uh, we have another anonymous question coming, and it says, when you say run an ensemble of your variable, is this not just dimension reduction?
No. And the reason why is what I was trying to get across, and I probably didn't explain it as well as I could have, was try and consider each individual feature as a potential model of its own. So you would do that on the front end. If you're talking about just knocking variables out with dimension reduction, I guess you could do it that way. What I was saying was more along the lines, there are a lot of folks who will take variables that have high correlation and they'll pick one and they'll throw everything else out. The problem with that is consider if you have purchasing levels, 1 month, 3 months, 6 months, 12 months. All those are going to be highly correlated with one another. The problem is they say very different things. The relationship you have with them 12 months ago versus the relationship you have with them 1 month ago are different. So instead of just saying, hey, all 4 of these are correlated, I'm going to pick one and throw the others out, you might want to be able to understand what is different in those elements. And one of the things that I've done, again, is use a decision tree. So take all 4 of those elements, stick them in a decision tree. So just those 4 together versus the target variable. Find out what ends up in the leaf nodes. And if you can eliminate inputs, fantastic, use it for dimension reduction. But I've actually found that the result of that tree is a much stronger engineered feature than the 4 put together on their own. Models are terrible at determining ratios. They're just awful. And all the automated feature engineering of the world has a very hard time with those type of relationships.
Okay, great. I'll move on to another question, which is around I think number 1, which is about the time. And it says, can you give us an example of how leakage appears when processing dates? Maybe
Yes.
A little bit of elaboration.
And by the way, about 70% of every client I ever had when I did consulting had leakage in their data and had no idea. So the best example that I can come up with is pretend that you are going to launch an email campaign in April. And you go through and you pull the data in March. Okay. The problem is if you have something in a counter that says like number of previous emails opened, great. And let's say you're going to analyze an even further back mailing campaign from December. All right, in December, if they opened an email, that counter goes up by 1. So now it's 1 higher. But the problem is you didn't know that before you sent the December mail. So if you've got data from December prior, and then all of a sudden you're saying, oh, but I've got this counter which continues to accumulate information over time, that counter continues to go up. So now you've got leakage of the results of the December campaign in your starting set for your data set. And it messes all kinds of things up. So one of the things to do is to say, okay, here's the hard line barrier. I'm not going to take any data prior to this date. And I'm going to freeze my data set. So on December 31st, everything's frozen. I'm going to take that and build my model in March, and I'm going to apply it in April. And that way you can't have leakage that happened after December 31st, but before March when you pulled the data and into April, if that makes any sense.
Yep, get that. Thanks.
You're welcome.
We have Mani asking a question about feature selection for the time series. So it says, what kind of feature engineering or feature selection or extraction can be done with the time series data? Is it going to be a difference?
There are differences with time series. I barely touched on smoothing, but that's a big component of time series. Actually, I'm going to make, let me think of the best way. There is a PDF that you can Google for of a book that came out many, many years ago, which was called Data Preparation for Data Mining. Fantastic book, no longer in print, but it is available as PDF for free download. Great discussions of smoothing and time series in there, highly recommended. If I had more practical experience on my own, I'd be more willing to jump into that, but that author did a much better job, so I'm going to let you go with that.
Good, good. And we have a question about tips number 6.
Uh-oh, I got to remember what tip number 6 was. Okay, we'll try.
Number 6, how do we use decision tree leaves as a boundary of bar charts? I'm not too sure.
Easy.
Yep.
Yes. If you follow a decision tree down, the one on the farthest left is usually the lowest value. So if I take years, or let's say months as a customer, and I plan my decision tree versus responded to the Mother's Day sale, what's going to happen is the tree is going to say, it was less than this, less than this, less than that. So those criteria are going to be the boundaries of the box. So if you take the conditions together, it would be like less than 3 months. And then the next terminal leaf may be 4 to 5 months. And then the next leaf node, so et cetera and so forth. So what happens is each box, if you follow the conditions down the tree, will actually give you the boundaries for the individual bins for your histogram.
Good. I move on to the next question, which is, what is a good way to encode sparse, high-dimensional, comma-separated features? I mean, history of URL visits for a user.
Prayer. Yes, that is a very common problem. It is a very hard problem. First of all, start off with reasonable expectations, because that's one of the examples I gave, which is P greater than N problem. So support vector machines is probably going to be one of the places you're going to visit in terms of algorithm. In terms of the data preparation, it's going to be tough. What I used to do is hierarchies of pages. So for example, product description pages for link together all the ones that had to do with sofas versus the ones that had to do with lamps, and try and group them together. You can try doing it with decision trees, but the problem is with highly sparse data, it's really hard to come up with great results. And part of the reason is people are remarkably individual. So the number of paths that people can take to the sales confirmation page is stunning. But that's how I would do it. I would try and if you look at the actual tree diagram of your pages, you can try backing up step by step until you get to the largest categories, group the pages that way, and see if you can get anything from that. If you have a 10,000 page website and you've got 7 people who purchased, it's probably not worth the effort.
Interesting. I'll move on to the next one. It's coming from Yasaman Sipanj. I hope I pronounced it correctly. Thanks for the question. And it says, if you have to run an unsupervised algorithm on your data and it hasn't produced distinct clusters, is it correct to assume that you need to do further feature engineering to improve the results?
It probably means that you don't have enough different dispersed data. I'd actually be really worried about that. You can sometimes have that in scientific observations. I would definitely try more feature engineering, but if you're not coming up with any type of clusters, check what your boundaries are for the number of clusters that you want to create and lower the number. If you're getting down and you're saying that you only want to have 3 different clusters from a data set, it's not producing anything, I'd be really worried about the data set itself before I did too much feature engineering.
Andrew Davis, he asked, after thanking for the talk and raising a question about tip number 7, when you say each node of a tree can be used in lieu of binning, is the benefit that each node is its own binary classification, and that new inputs can be placed into a node-specific model based on features used to build the decision tree?
You can actually create a single engineered feature. So let's go back to the idea of the months, for example. So what you can do is, let's say that you have your decision tree for a number of months, and we're trying to see whether they made the purchase on Mother's Day, and you've got the individual bins. What you can actually do is create a categorical variable out of that that says, oh, 1 to 2 months is A, 3 to 5 months is B. That's one way. The other way to do it is to do target mean encoding and to say, okay, if it's between 1 and 3 months, the actual mother day purchase rate was 12%. The engineered feature I'm going to use is 12% for that group. For the next group, 3 to 5 months, what was the purchase rate on Mother's Day for that? Take that value. For every record that met those criteria, that is the target mean encoding for that bin, et cetera and so forth. So you can engineer the features that way, because what happens typically in a histogram is it's going to either come up with an equal number of records in each bin, which is really not terribly helpful, or it's going to say, all right, I'm going to take some other thing to chop these up into 10 bins, let's say. And you may only have 3 important relationships. So if you use the tree and put really strict criteria on how deep the tree can go, the bins become much more meaningful, and therefore the derived feature becomes more meaningful, or engineered feature becomes more meaningful.
Great. The next question is something even I'm not sure if we need a clarification on the term, but hopefully you know that. It says, what is your view on digital twins type of model? Do you know anything about digital twins type of models?
Not a thing.
Yeah.
I will admit my complete and utter ignorance. I apologize for not being able to answer the question, but I don't know anything about that topic.
Yeah, the same thing. So if you can clarify more question coming down, then I would readdress this question again. Thank you.
And I apologize, but guys, if I don't know something, the worst thing I could do is give you an answer that's misleading. So I'm just going to plead ignorance and go on to the next one.
Okay, great. Diego Capozzi, thanking for the talk, and he has actually 2 questions. Let's
okay.
start with the first one. Could you clarify in more detail the process of letting a decision tree deciding the bin limits for transforming a continuous variable into a categorical one? I think that the question is more about the number of bins, I hope.
Well, you can actually, what you want to do is to control the depth of the tree based on the number of records, based on either the absolute limits. You can say, I only want a tree that's 3 levels deep or 4 levels deep, or you can assign a minimum to the number of records that appear in a leaf node or terminal node, so you can control how big it gets there. As a categorical, if you don't want to use the, if you just want to have like A, B, C, D, E, then the furthest most left leaf node is A, then B, then C, then D. So it becomes categorical that way, because the engineered feature only has values of A, B, C, D, E as opposed to number of months.
Okay. And the next question is less technical, but more political.
Oh, no.
Yeah. What is your opinion, the contribution of internal politics to the failure rate of data science projects?
It depends on the organization. In some cases, it's really big. Now, there are ways around that, however. And one of the ways around that is you've got to identify who your stakeholders are before you start analyzing the data. And you have to start working with them from the beginning. You can't decide after 9 months of analysis, oh, gee, we never told Susie about this project, and she really hates data science, so maybe we should have done something. That's not a good way to go. You have to get everybody into the fold on the front end and agree on the project before you start doing the analysis, or the project will never reach execution.
Next question is about in terms of targeting and coding. How do you find a way to time-based, which means average last n days target versus fold-based target encoding? Is that clear, or do you want me to read it again?
One more time, because is this based on time series data?
Yeah. So it says the targeting encoding, which is
target mean encoding. Got that part, yeah.
And then time-based target versus fold-based target encoding.
I don't understand the question. I'm really sorry.
Yeah, me neither. Okay, I'll go for the next one. Would you recommend to split continuous variable into bins based on model-like decision tree, random forest? I think it's just reiteration of what you said.
Yes.
Yes.
I would.
Right. Could you give some could you give some more example of solving class imbalanced issues?
Yes. Number one, if you haven't had background in class imbalance issues, it's a really good thing to research on the front end of the project and not on the back end of the project. So a class imbalance issue is where you're trying to, usually in a classification problem, you've got two potential. They bought, they didn't buy, they responded, they didn't respond, they were fraud, they weren't fraud. The problem is in most cases, there's a huge difference between how many people are fraud, for example, and how many people weren't fraud. The most infamous case I ever dealt with was a financial services company that had 1/100th of 1%, so 0.0001% fraud rate. So the total number of records they had was about 1 million, and I think they had 150 fraud records. So my first recommendation to them was don't try this project because I don't think you're going to come up with a whole lot that's terribly helpful. But you can't go in and say, yeah, I'm just going to throw all the records in there. So I've got 1 million records and only 150 are fraud, because what the model is going to do is say, hey, there's no fraud in here, and I'm right 99.99% of the time. And that's not helpful to anyone. What you have to do instead is to come up with ways to go around that. And the way that I was most successful with it is always undersampling the majority class. So whatever class is bigger, take fewer records from that and try and get it as close to 50-50 as you can between true and false for your classifier, and then build the model based on that, as opposed to trying to do it on the original data set, or you'll have all kinds of problems.
Yeah. For the next one is very linked, so I'm just going to repeat if you see any extra thing that you can add. So I appreciate methods such as power transform for continuous variables, but with class imbalance, is there much beyond class weighting or even capturing more data?
No, there isn't a whole lot more. You can oversample, you can undersample, you can try and use synthetic data. I don't recommend it. It's really complicated, and it has a high potential to mess things up. So that is not my favorite approach. I usually undersample the majority class. I don't try and create synthetic data. I don't try and multiply the records in the minority class, because you introduce all kinds of bias into the records the model's built on. That's my approach.
We have a very long question from Annabelle.
Okay.
I think she's very busy with this project.
Okay. I'm going to try for you, Annabelle. Here I am.
She says, I'm recently working on a data set has location information such as latitude and longitude.
Ew, okay.
But the values collected were so close to each other. So the model decided not to select these two attributes when doing the feature selection. But with my domain knowledge, I know these two are very important features. So the question is, if obtaining more data is hard, what would you do with these two features?
Lots of models will fail if you use longitude and latitude both as independent variables if you have any other data included, and that is not uncommon. There are actually transformation packages that you can download that will actually take your longitude and latitude, and even if they are close together, I mean, I don't know how close together they are. If it's a few feet apart, you've got a problem. But if it's like overlaying with a map, you have to use a transformation with the grid from a map perspective, and then be able to identify each of those locations separately. But longitude and latitude without transformation in a model, they almost always fall out as predictors. You have to use them together.
Okay. Scott, questions are still coming. Are you happy to carry on?
I got 7 more minutes, and then after that, if they have questions, if someone on the team can just email them to me, I'll try and get back to folks.
Okay.
Is that okay?
I need to reserve a couple of minutes at the end, so let's carry on for a couple of more minutes. So this question says, I think to some extent you have touched it already. Using techniques like LSTM to a time series problem, would a traditional feature engineering approach still give benefits?
I haven't worked enough with time series models and LSTM to be able to answer the question. the talk was primarily geared for classification problems. So that is where it's strongest. I don't have enough background with time series feature engineering outside of that reference that I mentioned, data preparation for data mining, to be able to offer a whole lot of help on that one, unfortunately.
Okay. And I have one more question here. It's coming from Paul. I was wondering whether you have some general advice on handling missing values. Is it worth spending a lot of time on coming up with fancy imputation modeling?
Boy, you really want to start a brawl, don't you, Paul? People have very specific feelings about replacing missing values. This is the approach that I've always taken. Either one, put them in their own, either have multiple models, one for those with missing values and one without. Or what I do is I always do the approach that we were talking about, using a tree or rule induction approach, and then having a separate classification for records with missing values. So for example, I've got state as an input. My engineered feature will use a tree for states that it does see, and then have a separate category for null values. I then put the target mean encoding rate of whatever the target is across all of them. I am not a big fan of calculating missing values. I am a super duper not big fan of dropping records that have null values if there's information content in them. My favorite example is the Pima Indians diabetes study, where people they didn't have blood pressure for, they just replaced it with 0. I don't know about you, but most of the people that I know that have 0 blood pressure are in very bad shape, and diabetes usually isn't the biggest issue. So please be careful.
Funny. There's a question not in Q&A, it is in chat, but I think it's worth mentioning. So it asks about how do you deal with many categorical values, like 80 or 800 unique categorical values?
Oh, okay. So we're talking about a single feature with high cardinality, or is it multiple features? Can we tell?
I'm not sure, but what I'm guessing is that when the number of variables are, and they're all categorical, and there are so many of them, this is how I interpreted it.
For a lot of algorithms, that isn't all that big a problem. Most of those are going to get eliminated. So again, if you apply my colleagues, oh, it's a single feature, right? Am I seeing that? Single feature with multiple values? Okay. If it's a single feature, that's when I use a tree, or rule induction works really well, like CN2 rule induction. So what it'll do is it'll take the all the features and then assign them to one of the groups, and then take the values from the bottom of the tree, from the leaf nodes, and use that as the engineered feature. And that works pretty well.
Great. So we have just a couple of minutes. Do you have any last comment talking to attendees?
Yeah, thank you guys so much for hanging in to the end of a fairly technical talk and giving up part of your day to participate. I really appreciate it, and thank you so much.